factorization channel, the thing has to split into two pieces. And it introduces an intermediate line out of nowhere, right? It's not there in the problem. So it gives you factorization. It tells you that it does exactly what an amplitude is supposed to do. And, but again, this, I haven't had a chance to show enough of it in detail, but I just hope you get just a flavor for how positivity and the sort of, and also when I said before, it's really logic and not so much geometry per se. It's just the logic of these things being positive. That's all that went in here. No specific values, nothing came in, right? It's just that if these things are positive, those things have to be positive, and it's that chain of logical deductions from positivity, which is what forces all of the correct singularity structure. Okay? So, yeah, so there is some dictionary. There's a little bit of a dictionary to establish between these forms of the amplitude, but the object is incredibly simple. The object is just generalizing a polygon into the Grassmannian. And the generalization of the polygon to the Grassmannian, what it looks like is walks and talks exactly like an amplitude looks like. Its boundaries are in the spots where amplitudes have factorization channels, and when you go to those boundaries, the object geometrically, literally splits into lower objects. There's one more generalization, which is to define which is to figure out how to geometrically ignore particles, project through particles. You literally start with a large amplitude and you want to forget about the presence of some particles, and learning how to forget about the presence of particles in a way that's compatible with the geometric requirements of positivity that turns trees into loops. Okay? But that's something I won't have time to talk about. So let me turn now to the question of the dual amplitude. So there's still much to be understood about the amplitude itself, its geometry, what its boundaries look like, et cetera, et cetera. But let's now move on to the dual. Well, maybe I should put a question mark. We don't know if this object exists yet, but let me give you some evidence that it exists, and I'll tell you a few things about it. Okay. So let's go all the way back to this form of logarithmic singularities on a triangle. So I promised you we take this form, so it was y dy dy abc squared over yab ycb. Oops. So in this picture, this is just I'm contracting, everything here is contracted with an epsilon symbol. So if you're not familiar with this, this is the sort of totally canonical form of lives on a projective space. And so in this picture, you really imagine you have this triangle sitting here, there's some point y, let's say there's a point y in here. The points A, B, C are fixed, you're moving y around, and this form has logarithmic singularities when it hits the boundaries of the triangle. Okay. Now, I can turn this picture, I can dualize it. So now A, B, C are lines, y is a line. I really drew it deliberately like this, so if y was a point inside the triangle, in the original picture, in the dual picture, it's a line outside the triangle. Okay? And now, let's say someone handed you a triangle. Now, with its vertices given, well, let's call it W1, W2, W3. Then, what is the formula for the area? Well, it's just the one we said before. It's 1 W1, 1 W2, 1 W3. But I can write this more projectively as W1, W2, W3 over Y, W1, YI, W1I, Y, W2, yw3. Where y is the line at infinity. So y would be 1, 0, 0, say. So if I choose, I can use GL3 to put y to be 1, 0, 0, so that y dot w is just equal to 1 here, right? So I'm trying to write this projectively, so I want to write it in terms of these three-dimensional vectors w, but it has to be invariant into rescaling each w separately. So that's why I have to have three w's downstairs, and so the y's have got to be there in order to make it make sense projectively. Okay? That makes sense. The area needs units, and the line at infinity provides the needed units. Okay, so that's the formula. That's the formula for the area of a triangle whose vertices are given. What if the lines had been given? What if the edges had been given? If that's A, that's B, that's C as the lines, then W1 would, for example, be the intersection of C with A. W2 would be A with B. W3 would be B with C. And so then this exact formula would be nothing other than ABC squared over YAB, YBC, YCA. Okay, so you see exactly what I said. This form of logarithmic singularities on the boundaries of the triangle is the area of the dual triangle. Okay? And ditto for the whole thing. So if you take a polygon, if you take this polygon P, our form, our amplitudhedron form with logarithmic singularities is equal to the volume area of P dual, with y being the line at infinity. Now let me be even more explicit about it. So what is an area? An area is just the integral of just the area formed on the interior. So the area of P dual is the integral over all the w's in the dual. So I can write it as w dw dw. That's the two-form measure on the projective space. Again, if I put w as 1, w1, w2, this form is nothing other than the usual dw1, dw2. Okay? So I take this over w dot y cubed, and then the w just lives on the inside of the dual. I need to have the w dot y cubed downstairs in order for the weights under rescaling to work out upstairs and for it to have the right units in y. So, let's summarize. In this case of a polygon, and more generally for the polytopes, we have an actual formula for this form. So on the one hand, we have P, then we have P dual. Okay. That will both be hexagons. Okay. And then omega P of y and z, the form of logarithmic singularities is, in fact, just to be very specific, is y dy dy factored out the triangle, an integral w dw dw over w dot y cubed, w on the inside of the cube. So this is the beautiful formula for the case of polytopes, polygons, forms of logarithmic singularity, and volumes. It doesn't look like it. It may not look like it so much, but in fact, this right-hand side is essentially Feynman parameterization. Okay? So if I take a simple version of this formula, I'll leave that as an exercise to you. Convince yourself that the formula we wrote down for the area of a triangle is otherwise known as Feynman parameterization. Okay? It tells you how to write the product of three denominators as an integral over something cubed. Okay? And it's an integral of something cubed over a projective space. that's exactly what the Feynman parameters are. When we write the Feynman parameters and we force them to add up to 1, it's really a projected way. It's a really way of writing something nicely projected. Okay? But on the left-hand side, you see, by definition, this thing, the only way I gave you to calculate this was to triangulate the polygon. I had to triangulate the polygon and add up the forms for each triangle. Okay? It's the analog of that we know how to do for the amplituhedron. Okay? We know how to give that definition to the form. However, that definition forces you to understand the geometry so well by hand that you can triangulate it. Okay? It's not very satisfying to give a triangulation-dependent definition of something that's triangulation-independent. This is the beautiful triangulation-independent form, right? And so that's why whenever we talk about the amplituhedron, we say that the amplitude is the quote-unquote volume of the amplituhedron. It's quote-unquote in the sense. It's the sum of these forms. It's a form of logarithmic singularities on the boundary of the amplituhedron, which is this dual cousin of volume. It has all the same additive properties as volume. But it's not the volume. I can't calculate it. If I'm dumb, I can't throw darts or use Monte Carlo in order to compute it like I could do the right-hand side. Okay? However, the form exists, most certainly exists. It's rather miraculous that it exists. It's not true that if I hand you a random space that there exists a form of logarithmic singularities on its boundary. Exercise, find one for a circle. Okay? There's no form of logarithmic singularities on the boundary of a circle. Okay? You can't just make up willy-nilly spaces and find forms of logarithmic singularities on them. The amplituhedron is a curvy space. The boundaries are in general, because we're involving Grassmannians, and we have these k by k minors. They satisfy nonlinear quadratic relations. It's a nonlinear space. So it's not at all obvious or God-given that it had to have a form of logarithmic singularity, but it does. Okay? So all of that is, so that's one motivation. Something like the dual should exist. The most obvious one, that we need to have an honest invariance definition of omega. That's reason number one. Okay. And in the simplest case, where k equals 1 and we just have polytopes, which we're generalizing to the Grassmannian, that definition involves the notion of the dual. Okay, so that's one reason we feel that whatever this definition is, has got to involve the notion of the dual. Okay, there's a second reason, which is that the final answer for the form, the final answer for the amplitude form in Y space has some remarkable positivity properties. Now I don't mean positivity in the sense of logarithmic singularities and fancy things like this. I really mean that the amplitudes are positive numbers. So let me try to illustrate that. We can see this already in the case of the polygon again. So let's say I'm triangulating the polygon, and I want to evaluate this form, but when y is inside the polygon. Okay? So I'm going to evaluate the form where y is inside the polygon. What's the answer? Well, it's that triangle plus that triangle plus that triangle. Okay? However, the contribution from this triangle is negative because y is outside that region. The combination from this triangle is positive, and from that one is negative. So when I do the natural triangulations of the polygon, term by term, they're not positive. I mean, I just mean numerically positive. If you evaluate it, okay, they're not numerically positive. Some terms are positive, some terms are negative. And yet the final answer is always positive. Okay? Why is the final answer always positive? It's because of this formula. And this formula is obviously positive, right? It's the area. That's why it's positive, right? Now the fact that there's some here that are positive and negative, you also see in another amusing way. So let's say you start with a triangle, and then you add some fourth point. Still convex. So the amplituhedron, in this case just the polygon, is just getting bigger, right? The space of the actual amplituhedron is getting bigger. I add a fifth point is getting bigger. Sixth point is getting bigger, right? But let's say I leave y in here inside the first triangle. Okay? The amplitude itself is getting bigger all the time. But if you compute the form, you find the form gets smaller. It's always positive, but it gets smaller as you add, as you increase z. Again, it's obvious in this picture because all the new triangles that you're adding, y is outside them, and so it's negative. Now, what does this look like in the dual picture? In the dual picture, you start with a triangle, but each triangle that you add here is something that you lop off there. So the area is getting smaller. You lop off this one, so the area is getting smaller, and so on. Okay? Adding triangles in this picture is lopping them off in the dual picture. That's why as you add points, it gets smaller, despite the fact that it always stays positive. So those are the sort of things that we can look for in the answer, since we know the answer. Right? We know the answer at trees, loops, up to umpteen loops, trees for pi, n, and k. Every place that we've looked, when y is evaluated inside the amplituhedron, the integrand is positive. This form is positive. There's always a sum over positive and negative terms. Even in the cases where the positivity of the external data doesn't matter at all, like 4 points. 4 points multi-loop. 4 points multi-loop, starting at 4 loops. In every local way of writing the answer, there are positive and negative terms. The sum magically is always positive. Okay? It's almost 50-50 how many are positive or negative, but the sum is always positive. So the positivity is the second big clue that there is something missing, that we need to find something like this dual to explain why things are positive. And the final, this isn't so much a clue, but it is a desire. So we all know that we like to do the integrals. Now, of course, you could have the perfectly sensible attitude that if you just want the final answer, who cares about getting the integrand? Just go straight for the final answer and forget about this intermediate step of finding the integrand. So why do we care about the integrand to begin with? I think we care about the integrand because it's only when you have the integrand that it's clear that what you're talking about has something to do with gluons. Okay? In other words, someone just hands you a final answer. However they got it, beautiful polylogarithmic functions, but they just hand it to you and say, is it obvious that this thing is this obvious that it is local and unitary? It is not obvious that it's local and unitary. You have to take it, you have to look at the discontinuities, you have to check that all the discontinuities, the optical theorem is satisfied, and so on. Okay? It's not, however you get it, it's not manifest that all those things are true. In perturbation theory, what makes those things manifest, much more manifest, are the simple, sharp singularity properties of the integrand. And it's that whole structure which has been geometrized by the amplituhedron. So that's all the amplituhedron is. It's the geometry that tells you ahead of time where all the singularities are, just as a consequence of this positive geometry. So it seems to me that a sort of complete understanding of the physics should tell you how you go from that object to the integrated objects. And of course, you're not going to want to sit with the objects as given, certainly not as handed to us from these triangulations and so on, in order to try to do the integrals. At least all the attempts that we've made over the years to do that haven't seemed particularly nice. I think what's much more likely, especially at loop level, is that these representations, these sought after, we don't have them yet, but these sought after representations of the forms are like a smart version of Feynman parameterization. They're not random Feynman parameterization, but they're the correct, some correct, tailored to the theory form of Feynman parameterization. Why do I say that? It's because, you see, especially when we go to loop level, we'll have these y's and we have ab's as well. We have all the loop integration variables. That's what the amplitude forms are. And if any such formula exists, the entire point is that the dependence on AB is made totally trivial, right? Just like we said, this formula is a simple example of Feynman parameterization already. Okay? So if we have it so that all the dependence on AB is trivialized, but we have to integrate, but all the dependence on the external data goes into specifying boundaries over the region of some other integration variables, then we can do the integral over the ABs easily, just like with finite parameterization. And we'll be left with an integral over these other variables that are parameterizing the dual amplitude. So let me say it again. The hope is that the integral is that once you represent the, especially at loop level, once you represent the loop form in this dual way, that the integrations over loop variables will be trivial, and you'll be left with an integral over the dual amplitude variables. And that the dual amplitude variables are a intelligent, tailored to n equals 4 super Yang Mills version of finite parameterization. Now, why does that smell right to me? It smells right, and I'll just say this. So we have the amplitudhedron, and as I said, the amplitudhedron, even though there's it's a basically perturbative object, and it tells us about the integrand for gluons. Okay, so of course there's no Hilbert space, space-time, blah blah blah, but the object you get is the same as the object you get summing up the Feynman diagrams for gluons. Now, of course, there's the ancient picture that the way gluons turn into strings is by drawing planar diagrams and having these things, especially in strong coupling, condensed into world sheets. Okay? And if we're super powerful and could, supposedly if we're super powerful, we could sum up all the Feynman diagrams, then we could start seeing this happen, right? But what is that picture supposed to be? That's not supposed to be a picture. That's not supposed to be a standard quantum field theory picture. That's like a world-line formalism picture, right? That's a picture which ultimately is supposed to condense into the world sheet. But we know what are the variables along those little world lines? They're Schwinger parameters. They're Feynman parameters. Okay? So there's some smart version of Schwinger and Feynman parameters, which lives on these pictures, which wants to, at strong coupling, turn into the variables that parameterize the world sheet. Okay, so that's super vague, but that's been a super vague fantasy for a long time. Right? Is that somehow these pictures turn into a picture of strings at the other end. So since we know we have a duality between gauge gluons and strings, and the amplitudhedron is telling you, the amplitudhedron is the invariant way of capturing the gluon part. By symmetry, there has to be some object that captures the string part. And given that to go from here to there somehow needs to bring the Feynman parameters into the game, and given that the Feynman parameters seem in this fantasy to be plausibly related to the dual amplitudhedron variables, that is the hope. The hope is that the object on this side that connects to the string picture is the dual amplitude.
The string sounds like strong coupling.
No. So in fact, that's actually the point. Is that the amplitude itself is we don't have a G in town. We have a separate object for all the different loop orders. And what I really mean isn't maybe necessarily strings. Maybe I mean flux tubes. Maybe I mean the integrable structure that all our friends see at the
Derivative analog of Feynman parameters. Then,
yeah. Ultimately, yes.
The usual ones are very tied to a very.
Yes. Certainly. Yeah, certainly. Yeah. So this is all. I mean, this part is all fantasy, of course, but it does seem to be, from many points of view, something natural is missing paired with this, and both from an internal to its own logical structure, trying to find these forms some data of some remarkable positivities that have to come out, as well as the more general ideas. Seems like that's the sort of thing that we should be looking for. Now, I have 5 minutes, so I haven't told you anything about it. But let me at least tell you one thing about the steps that we're taking to start trying to discover what this guy is. And I think much stronger evidence now that it actually exists. Okay. So to do this, let's go back one last time to our picture of a polygon and just see what it is that we're doing here. Okay? So here, we have a polygon, and we gave one description of the interior of the polygon in this way. It's the image of C dot Z with all the C's positive. Okay, now, amongst other things, this is a very inconvenient description to actually check whether a given point is in the polygon or not. Someone hands you a point and says, this is a point in the polygon. You got to go check to see, can I write it as C dot Z with all the C's positive, right? It would be much more convenient to be able to just say, no, just have a more efficient check to see whether it is or isn't. And in fact, there's a second description of what the points in the polygon are. This description makes the vertices special, but there's another description that makes the edges special. I just say that y, zi, zi plus 1 are all positive. I just say that y is on the right side, is on the same side of all of these boundaries. So this is a second description. In fact, in complete generality, whether or not the z's are positive or not, this definition, you have this definition of a polygon or a polytope, but you have another definition where CA, ZA, or y dot some, or yi, WAI are positive. These are two different descriptions. One of them involves the vertices, the other one involves the boundaries. And even in this most trivial case of the polytope, it's not 100% obvious that if you have y equals C dot Z, that it's possible to find a bunch of W's such that y dot W is positive. Okay, that little thing is called Farkas' theorem, and it's one of the first things we prove about polytopes in the polytope 001 course. Okay? It's not 100% obvious. You can prove it, but it's not a one-line proof. Okay? Now, I'm bringing this up just so you see that this already is the beginning of finding what has to go into the dual. Because this description in terms of inequalities knows about the dual polytope. In fact, this is another way of saying what this theorem is telling you, is that you can describe the polytope or you can describe a dual polytope. And what goes from one to the other, from the z's to the w's, are exactly what tells you what to go from the linear combination description to the inequality description. So we can ask whether, and so you see this is also convenient. So if someone hands you a point, you just check whether all these inequalities are satisfied or not. Okay. So you can ask the question, is there an analog of that description for the amplituhedron? Okay. Can we define what the amplituhedron is strictly by giving a bunch of inequalities? Okay. And there's an obvious one that you can try. You can try that the y, so you have y1 up to yk, I'll abbreviate that as y in general, yi plus 1, jj plus 1 is positive. Okay. So that's being on the right side of all those boundaries. And we saw if you're in the amplituhedron, that's always true. In one direction, it's But you can say, is that all it takes? You just impose that you're on the right side